Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 6, 2025. This paper landed just yesterday. The standout result is a diffusion decoder that works in a single step without adversarial training, improving reconstruction FID from 0.87 to 0.50 with 1.4 times higher throughput, and keeping DIT generation quality while making sampling 3.8 times faster. The paper is titled SSDD, Single-Step Diffusion Decoder for Efficient Image Tokenization, and as we will see later, the implications for model training speed are significant. It couples a hybrid U-Net plus transformer design with flow matching, perceptual losses, and lightweight distillation to serve as a drop-in replacement for KL-VAE tokenizers. Alright, the introduction highlighted faster sampling and better reconstruction. Figure 1 presents the speed versus quality trade-off, where images per second rise as RFID drops, and the SSDD curve sits on the Pareto front across model sizes. The right panel shows side-by-side reconstructions, where textures on the clock and the dog look crisper at similar throughput. The bottom diagram sketches the pipeline, with a multi-step diffusion teacher distilled into a single-step SSDD decoder so generation stays fast and faithful. Well, Figure 1 showed the speed and quality gains. Figure 2 presents the training pipeline. The encoder maps the image to latents, noise is added to create a noisy input, and the diffusion decoder denoises while being conditioned on the latents and the time step. The middle transformer plus U-Net block carries the heavy lifting. The right side illustrates targets and one-step predictions. Training combines flow matching, perceptual LPIPS, and REPA feature alignment, so decoding stays stable and sharp. Alright, the previous figure covered training dynamics. Table 1 reports reconstruction and speed, and the single-step SSDD wins on RFID, LPIPS, and DreamSim across encoder configs. With F8C4, SSDDS reaches about 1,000 images per second with RFID 0.50, while SSDDH matches epsilon-VAEH at 0.38 but runs roughly 3 times faster. Similar trends hold for F16C16 and F16C4. So the previous table highlighted speed and reconstruction. Table 2 summarizes scaling on ImageNet with an F8C4 encoder, listing parameter counts and RFID and LPIPS at 128, 256, and 512 resolution. The SSDD family consistently beats the KL-VAE and epsilon-VAE lines, which shows stronger perceptual reconstructions at similar or lower size. SSDDH reaches about 0.38 RFID at 256, with LPIPS near 0.050, while SSDDM already delivers about 0.42 and remains competitive at 512. Okay. Table 3 evaluates image generation with DIT XL over ImageNet at 256 resolution, reporting GFID and images per second with and without classifier-free guidance. Across encoder settings, the SSDD decoders deliver lower GFID and higher throughput than KL-VAE and ditto. The right margin annotation highlights a 3.8 times speedup. F16C4 with SSDDL runs about 12 to 22 images per second with guidance, while F8C4 with KL-VAE sits near 3 to 14. So the previous table emphasized generation speed. Table 4 reports an ablation that stacks changes on a ditto small baseline and tracks RFID, PSNR, and DreamSim, plus the number of sampling steps. Adding the SSDD medium decoder cuts RFID by about 1.2, and the REPA loss removes another 0.44, which signals stronger generative fidelity. Distillation slightly worsens RFID yet collapses sampling from 8 steps to 1. AGAN loss does not improve the metrics meaningfully. So, the previous table tracks step reductions and metric shifts. Figure S5 shows a qualitative side-by-side comparison across decoders, which highlights texture fidelity and edge sharpness at match throughput. The leftmost column shows the originals for reference. The two rightmost columns present SSDD8 medium and its distilled single-step version, which produce crisp clock numerals, cat fur, sign edges, cabin windows, and flower petals, while KL-VAE and Ditto B plus LPIPS look blurrier or distorted. Wrapping up, 2 takeaways stand out. The single-step diffusion decoder delivers higher perceptual reconstruction while running faster, and it achieves that without adversarial training. The broader implication is clear. A drop-in replacement that can speed training and sampling across latent pipelines while improving visual fidelity. That is it for the AI Research Roundup. I am Alex. Thanks for listening.